Good morning, everyone. This is the John Chappell Natural Philosophy Society Saturday Science Chat. I am your host, Franklin Hu. Today is February 10th, 2018. And if this is the first time you're joining our group, we invite you to check out the resources we have on our web, including our website, which is naturalphilosophy.org, and you can join us and become a regular member of our group. We regularly discuss a lot of things in the forums and email. So, and also check us out and give us a like on Facebook. So today is an open forum. So if you guys got some questions, you can put them in the chat or just wait till I ask for open questions. Although the first thing I thought we would talk about, since we didn't quite get through all the questions and answers in our last video chat, was questions about the atom. And so I asked Bill Lucas, what's a list of things that any atomic theory needs to explain? So we just came up with a list. So let's initially just go through them, and then we'll go through each one of these in detail. So we have emission spectra. So when atoms are excited, they exhibit a very, very specific set of lines and we call that the emission spectra. There's also the associated absorption spectra. And another thing to be explained is that when atoms form molecules, we can precisely measure those angles, and we should be able to explain, what are those angles? We have the ionization energy. So when we apply energy to an atom, the electrons start flying off, and we can measure fairly precisely how much energy it takes for each electron to come off of that atom. And they come off in very specific patterns, and they come off in very specific groups. So we need to explain that. We need to be able to explain when things decay, why do they decay, and what do they decay into? And related to that are the list of the known isotopes. So you can't add an arbitrary number of neutrons to an atom and still have it be stable. And there are some isotopes which simply do not exist. So there seems to be a limitation on that. You should be trying to explain, why is it that you can't stick like 23 neutrons onto a helium atom, and that just doesn't work. We should be able to explain the mass of the atoms. And there is evidence that you have to explain showing that there is no weak or strong force in the atom. And there are patterns. There are a lot of patterns in the atomic data. One of them is called the islands of nuclear stability. And they have like a chart of these things. Related to that, there are the so-called magic numbers, where we find where the most stable isotopes exist at certain shell numbers, or a certain number of neutron numbers, or a certain number of proton numbers. Another thing to explain would be the scattering data. The most basic that was done by Rutherford, and he was the one who determined that the nucleus is this tiny little ball which only contains the protons. Although that is the conclusion, what you do need to explain is the scattering data showing that you get high angle scattering that has to be explained. And atoms also have very measurable characteristics, such as spin and the magnetic moment. So, and actually there are probably a lot of other things which you could explain. So So this is an area of my expertise, since I claim to have an atomic model. I guess Bill, you also have an atomic model.
That's right.
So I'd like to hear each one of your explanations for these things. Is there anyone else on the call here who has a specific atomic model?
I have a model. It's not so explicit, but it's used on the fact that all these atoms are constructed from elementary particles. So most of the properties that atoms have come from these constituents. For example, the mass, the electric charge. Um, they don't have color charge because if the elementary particles bind, they only bind in colorless things like hadrons. So atoms don't show color charge. Only elementary particles can show color charge, but atoms can show spin because you can add up the spin of the elementary particles that constitute them, and you get the spin of the atom. So I think it's smart to start at least with the elementary particles because most of the properties of atoms come from these things.
Hans, when you say that an atom has spin, do you mean the nucleus or the atom as a whole?
The atom as a whole.
So the atom as a whole has spin?
It has the spin. It is a sum of the spins of its components.
Okay.
And there's another thing, and that's, to my opinion, very important. Everybody is talking about wave functions, but the wave functions are, in fact, an indication that stochastical processes are controlling the whole binding of elementary particles into atoms. Stochastic processes are a very important part of physics, but contemporary physics doesn't treat them. It only looks at the wave function and stops thinking anything further. But in fact, the wave function hides what's below of it, and below of it are stochastic functions that are spatial Poisson processes that are a combination.
Tell us what a stochastic process is.
It's something that generated a statistical. It can be a rather well organized statistical distribution. For example, it can generate a Gaussian distribution. You know what the Gaussian distribution is? It is a normal distribution in statistics.
Yeah, I know what that is.
And you can have that in 3 dimensions. It is a combination, for example, of a Poisson process and a binomial process, where the binomial process is the Gaussian distribution.
Well, I have a comment on Franklin's opening statement.
Good.
Can I make a comment on your opening statement, Franklin?
Sure, go ahead.
You say, you use the word explain, and science doesn't use the word explain. Science uses the word predicts. Science makes predictions from models. It doesn't explain anything. Modern science doesn't explain. So your whole thesis about using the word explain is, in my opinion, misleading.
Well, I would completely disagree, because I think it is, in fact, the purpose of science to actually explain things. Now, the theory that you just gave with science...
That's your claim, but that's not what
my claim.
That's
but
not
modern
what
science, But modern science does exactly what you say. I know. I'm explaining to you that modern science has completely abandoned that.
Your whole thesis is essentially misleading the audience.
No, I would say that that is actually one of the ways that science has actually run off the rails, and that we have
Well,
completely
that's just your
abandoned.
thesis, but that's not anything of what Hans isn't even talking about explaining things. He's
No,
talking
no.
about statistic processes.
Yes,
Physics is only describing things, and it can use mathematics to combine these descriptions and make some combinations so that you can also uh, find things that are not yet observed by combining these observations with mathematical methods. But that's not explaining the origin of why these things are behaving like they do.
yes, and I think this is a very important point,
Yeah,
which is which is
physics
that
doesn't explain; it only
physics,
describes.
yes, physics has completely abandoned the idea that you can even try to explain the exact mechanisms that physics has been lost in this morass of mathematics, where good physics is counted as you can predict the result of the empirical result, and that's really all that matters. Now, I feel that that's wrong. Personally, I feel I mean, I don't believe science worked that way
So what do you
prior
mean
to
when you
about
use the
100 years
word
ago.
explain? What is the use of the word explain mean to you? I mean, to me, as soon as I hear that word explain, I have no idea what you're talking about.
Okay, well, that's a good point. So, explain means that you can form a chain of logical conclusions which allow you to describe the actual reasons behind the empirical result. For example, we
So
back
now
in
you've
the ancient
introduced
days,
actual reasons. What does actual reasons mean?
well, actual reason, for example, I had to give an example. Like we have this substance called water, which has been around since caveman days, and caveman cannot explain what water is. So, what does an explanation of water mean? Well, you have to have a series of logical statements which all line up, which will give you an explanation for the properties of water. So, in order to do that, as scientists, we first have to discover the statement that all matter is made out of smaller bits, which we call atoms. And furthermore, we have to categorize and discover what all those little bits are. So at some point, we discovered that there's this thing that acts uniquely, which is hydrogen. And then we found this thing that uniquely exists called oxygen.
Franklin,
Now we found.
these are still
Can I please
descriptions
ask someone? Can I
and
please ask
combinations
a
of
point?
descriptions.
Can I please ask a point of order here, which is that when someone is making an explanation, that you please not interrupt the middle of that description. Can we please do that? So at least wait for me to
Well, if you wouldn't
end my sentence.
basically act like a tank and just keep talking and talking and talking about when you're saying things that don't make any sense to other people. So give other people a chance to say something rather than you dominating the discussion. Hans
But
wants to make a comment.
I'm in the middle of making an explanation, right? I'm explaining how people
It's just a lot of words that don't mean anything, Franklin. I mean, you go on and on. Give other people a chance.
Well, don't you think it's rude when people just break in while you're trying to explain something and completely,
You're
don't
not
give you a chance
explaining,
to
you're
explain?
lecturing.
Well, is there a difference between lecturing and explaining?
Well,
I mean, I'm trying to explain something. You asked the
just give
question.
us a break, Franklin. We've heard it all before.
I mean, you asked the question, like, what do you mean by explain?
You
And
just
I'm
go on for
explaining.
10 or 15 minutes. I mean, come on.
I just went on for like 2 minutes before someone tried to interrupt me. I mean, it's just a point of order.
This
Just
isn't
wait
a
for at least me
forum
to
for you
finish
to
my
talk about
sentence.
what you think the world ought to be. It's not a forum for you to express your opinions.
Well, in
Okay.
fact, this isn't a forum for everyone to
That's
express
the
their opinions.
problem. You're supposed to be the moderator, not somebody who pontificates about your opinions.
No, that's not true because you just asked a question
Well,
and
you're
I'm trying to answer it.
pontificating. You started
But
off at the very beginning pontificating, okay? And what I really would like to know at this point is there, from Bill Lucas and Hans and people who are kind of knowledgeable about this, my particular question is what we're really talking about. Where you use the word explain, I think the word model ought to be used. And my question is there a single consistent model that's used to explain atoms, or do they have to use a number of different models to explain different aspects of the atom? And that's kind of what I would like to know the answer to.
well, I think you're correct. I mean, that what I was trying to get to was a model. This is what we mean by explain, that you can put together something, perhaps even something you can physically see, like we have the model of molecules and atoms, and that by that way, we can explain what water is. So that's what we mean by explain. And last week, Bill mentioned that there are two major models of the atom. There is the shell model of the atom, where
Nucleus of the nucleus.
okay, of the nucleus, there's a shell model, and then there is the liquid drop model, where all the nucleons are just literally like a liquid drop, and they kind of break apart like liquid drop. And the shell model has very, very specific locations for each of the nucleons. So there are these two completely different and actually contradictory models. Both of those models can't be true at the same time is the main problem. But yet each one is required to explain some part of the atomic data. Is that
By
correct, Bill?
explain, you mean model.
Yes. I would like to say, Frank, that there's another issue we're not completely addressing. It is the
We're getting a
science.
big echo out of you.
We can't hear you, Bill.
You can't hear me?
There's
No.
a very large echo. Let me see if I can mute some people. Okay, go ahead, Bill.
Okay. There is in the scientific method, we have had a major change in modern times. The scientific method used to be based entirely on logic, and that you had assumptions or axioms that you used to develop your theory, which you then used to predict data. What we have done is we have changed that. In the past, if any of your assumptions or axioms were proven false by experiment, then the theory was proven false. But today we have taken that role of logic out, and we say only the predictions of the theory can falsify it. And then, like in the theory of general relativity, when it couldn't explain the gravity of uh, uh, spiral galaxies and the forces and the motion of the arms, they invented dark matter to rescue the theory. So they didn't falsify general relativity. What they did was they invented dark matter and dark energy, which composes 96% of the universe, but we've never seen it. But that's not good. You should falsify the theory of general relativity because it cannot explain that, and that's its domain. And they rescue it. So we have a lot of things going on in science. We have rescuing of theories, and we're trying to defeat the role of logic, and so that nothing that's in modern science can be considered true. In fact, I'm publishing a series of articles right now in Common Sense Science newsletter, and I'm showing all the major theories of modern science. This is in chemistry, biology, geology, astronomy, physics, all of them since about 1840 are known to be false. And
So we're in big trouble.
we're in big trouble, and we got to look at the source. The source is, do you use logic, or which is the way you discover truth, or do we just use our opinions and forget about having to agree with the data?
Well, the science agrees with the data. It's just that the models that they're using are not really constructed. They're, I don't know what the word I would use.
Let me give you some examples where we don't agree with data. There's no theory of the atom in any textbook in the United States that can predict 50% of the atomic data. 50% that they miss. Why is that? They said, well, that data is no good. It doesn't agree with our theory. That's what they say.
Okay, what do you mean by data, Bill? Are we talking about the nucleus, or are we
I'm
talking
talking
about?
about the emission spectral lines of the
Here's
atoms.
a list.
All right, okay, we've talked about this before. Okay.
Right. And
Now,
so
what about in the nucleus? This is kind of, I think we understand the issue about the in the electrons. What about in the nucleus? Is there a
the nucleus, the spin of the nucleus, which is measured, various nuclear isotopes, is measured, and no theory of the nucleus can predict 1,500 of the nuclear isotope spins.
okay? So basically, there's a issue there with the credibility of the models.
Well, see, the assumptions of the model, the axioms as we call them, they are false. And we have the shell model and we have the liquid drop model. Both of them, their complete set of axioms is false. And they should be thrown out as a theory, but we don't do it because we like the results of the theory. It satisfies our politics, I guess you would say. And so this is, and it's not just the atom and the nucleus, it's the theory of elementary particles. There's so many theories of elementary particles, and none of them can be falsified. And
So what we have is a grab bag collection of different theories and models.
right.
And as long as, if I want to make a prediction, or if I'm a scientist and I want to make a prediction, I can just pick a model out of the whatever my favorite model is that I think is the best model, and use that. And then I make predictions and I compare that to the data, and it looks like it works pretty good. So I say that's okay. Is that what they're doing?
Yes, but they know that their model is based on certain ideas, and they know that those ideas are false, and they know that their model is not true. But they just want an approximation.
Right.
Yeah,
So
I
all
think
we're dealing with are models that make close predictions, reasonably accurate predictions.
But now we measure these things to 8 significant figures. Do you know how many theories predict the data to 8 significant figures?
Well, you told us this before.
0. That's because
I
based on false ideas.
mean, it's trivial to falsify the liquid drop and the shell model simply because they are incompatible with each other. One of those two has got to be wrong. But yet,
Both
they're doing exactly what Harry said, which is they're just picking their favorite theory depending on what part of the atom they're looking at, and say, oh, well, we'll just pick this one, right?
liquid drop model does the heavy nuclear isotopes, and the shell model does the lighter nuclear isotopes. That's
So
basically.
you have different ranges of applicability, which is sort of like Newtonian mechanics and special relativity. They have their range of application, and you pick whatever works best in the range of application.
But the problem with like general relativity and special relativity is they ignore the fact that you can't have a successful, possibly true theory unless you take into account not only the velocity effects, but the acceleration effects and the radiation reaction effects. And they don't. So we know they're incomplete, and you do look at the right kind of data and you see it doesn't work at all. And so we know that, but we're not willing to say, well, logic tells us these are false, and we need to have a theory that includes all these other effects that are related to acceleration and radiation reaction, which is dA, the acceleration dA over dt, time derivative acceleration. But we don't do that. So there's so much politics going on in science that none of the current theories of what we call modern science are valid. They have to be falsified because they're not using logic properly.
Okay, so let's get back to explaining, our list of like 13 things to explain. So,
I think the word is predict.
well, I would say the word is explain.
Well, right there, I think we're at an impasse.
Well, it could be.
Well,
I always attempt to explain.
logic can
I
falsify
think science can explain those things. They just pick a model that explains it, and then they're done.
But see, the model can be falsified by logic, no matter how much data it explains, if the assumptions involved in the model are known to be false.
I understand that, Bill, but the point I'm making is that if you use the word explain, then I can explain what happens in a particular set of data perfectly, to 8 decimal points. Okay, but given another set of data, I might not be able to explain it at all. You see what I'm saying?
Yeah, but you see, unfortunately, in science, you've got to explain all the data with your theory.
Right, I agree with that. But my point is the word explain is ambiguous. That's my point.
Explain is going back to logic. Logic enables you to discover an explanation.
Well, I see your point. I just think the word explain is too colloquial, and I don't think it has a specific scientific meaning. That's my view. You can take that view if you want.
Yeah, I think you have a point there. It's not a precise scientific way of looking at things in some sense. It's more qualitative.
I mean, I don't think we should get our axles wrapped around definitions, which people tend to do.
Well, my point is, Franklin, that you can use the word explain to mean a lot of different things. If I was a mainstream scientist, I would say, like special relativity explains every experiment that's ever been done. Of course, we know that's not true. But from his point of view of what he means when he used the word explain, it's perfectly valid for him to say that.
Well, I think the difference was the opinion that you thought that science only predicts, which I believe is differently than explain.
What they claim is they create models and make predictions based on those models. That's kind of the way they're talking about it. Okay, explain is really, I don't know what that word really means, because I can think of a lot of nuances of the word explain that are not really, science doesn't even deal with.
Well, explain also, a model has to be based on something, and so that those ideas that the model is based on are where you get your notion of an explanation. And the model might produce an equation, but what does the equation mean? What is it based on? What ideas? And those ideas are your explanation. And
I agree with that, Bill. The problem I have with that is that science doesn't really deal in that, because
today that they used to for thousands of years.
I agree. But tell me what electricity is. Tell me what magnetism is. You go into a textbook on science, they're not going to tell you those things.
Because that's one of the things they cannot explain.
They're just going to give you equations that you can use to make predictions of calculations, and but they don't tell you what an electromagnetic wave is. They don't tell you what electricity is. those things are not in part of the discussion. They're not even in textbooks.
I would say that's because I cannot explain them.
They used
Well,
to.
that may be a reason, but they're not really part of the scientific discussion. Explanation isn't really part of the discussion.
You know what Ampere said the field was? He called it a spirit. And guess what the spirit was of? God. So at the time that electrodynamics was being developed in the mid 1800s, we did have qualitative explanations, and they seemed to agree with the Bible, but scientists didn't like that, and they didn't do that, and they came up with a totally different way of doing science than Ampere started with.
Well, let's see here. I mean, I think this is an important discussion about, what models means and what explain means. Now, when you ask about things like electricity, like I said, I don't believe that that's in the textbooks because we have no good explanation. But then again, I think that's where science went wrong, and that we still need to be able to, that still needs to be part of our science books. But getting back to the data that we have on atoms. So a website I always go to, are you guys able to see my screen? Are you seeing the web elements periodic table? Okay, so this website has the periodic table, and you can click on each of the elements, and it gives a lot of data on the things that we've been talking about. So if I click on hydrogen, first of all, on the very top, they show the atomic spectra. So if you put this hydrogen gas between two electrodes and you zap it, and you look at the bands of light that come out.
Franklin, I don't see it. It's not on my screen.
Okay, there may be a lag, so I may have to wait for you guys to see this. But you're not seeing, like, I just clicked on hydrogen, and so you tell me if and when you see it switch over, because I'm not sure why it's so slow. So you're at this point, you're going to have to imagine this, but I'm sure you've seen these spectra pictures where there's only very specific bands that come out. And so for hydrogen, there are really only 4 visible bands. So that's what we mean by the emission spectra. And now the reverse is also true, that if you shine like sunlight or some wide spectrum light through the element, that you will see it will also absorb very specific spectra. And I believe it's just the reverse of the emission spectra. Is that true, Bill, or is the absorption spectra different?
Well, you have different processes going on. You have to take into account radiation reaction, the recoils, and that sort of thing. And so there's going to be a slight difference. Just like, if I throw a ball, it's a certain effect on me, but if I catch one, that's a little bit different. And if I radiate some more energy off, some more light, as a result of recoil, like for instance, if a gamma ray or something like that comes into an atom and is absorbed, it's going to recoil, and you're going to get an effect. You may even get emission, a slight emission of energy as a result of that recoil. So you've got a lot of different things you've got to look at, and we do that in science, and we have a lot of data of that sort. And so, but they're very similar. Yes, very similar.
So this is a very peculiar thing, that the spectra is quantized like this. So what is your feeling about why we have this quantization?
We have 2 approaches that have been done. I don't know if you realize it, but the current theory of quantum mechanics was developed in Copenhagen around 1927, and they had big debates among the scientists, and uh, the debates were related to the assumptions and the models of what uh, an electron was. And uh, there was a fellow named Parsons who said that the electron is in the shape of a toroidal ring, and you can explain uh, the various atoms that combine to form molecules with this model, because the electron doesn't orbit the nucleus; it's in a fairly stable position, and that way it can they can form the chemical binding that you need between atoms to form molecules. And the people in chemistry loved that because they could now explain all the models of the uh, molecules and how
But
atoms.
spectra would seem to be very uh, distant from
But the
the
other,
molecules.
let me finish the other model um, was the point model with the wave function. Now, the wave function for the electron was measured by Arthur Compton. And guess what it was? The circumference of Parsons' ring. And so the various wavelengths of the different shells and electrons in different shells was found to be related to how the waves were set up in this toroidal ring. And the waves, if it was one wave around the ring, you had a certain wavelength. If it was two wavelengths around the ring, you had something else. If it was a half a wave and it took two revolutions to make a state, you had all of these states. And that was explaining all the so-called shells of the regular quantum mechanics that we have today. But there was the question: do we have a physical explanation for this, which means a toroidal ring, or do we have a mathematical explanation with no physical model? And that was what we have today in terms of our quantum model of the atom. The Dirac model of the atom is uh, of that sort. Uh, so we
So you're
have
saying that the resolution was a mathematical interpretation of the atom.
no, the resolution
So the
was a politically determined thing that we would go with no physical model of the electron. It'd be a point particle, and we would use quantum mechanics. And the reason for that was very interestingly. It was people reacting to what was called the Second Great Awakening, which occurred in the 1840s and up through 1930 something. And this reaction was, we don't want any explanation in modern science that could be supportive of something like the Judeo-Christian scriptures. And so that was the guiding light. And people like Einstein objected to that, at the Copenhagen presentation, Copenhagen meeting, where they were voting on what they would choose. They had both models. There were representatives there from both Oxford and Harvard and MIT who wanted the physical model, and there were people from the European side that wanted the quantum model, which had no, it wasn't based on physicality. It was based on mathematics.
uh, Bill, let me just ask a question. What about the Heisenberg matrix mechanics model? Is that really distinct from the Copenhagen Niels Bohr model? Is that like a different quantum mechanics, or what in your view, what is the matrix mechanics model? Do you understand what I'm asking?
Yeah, it's part of the mathematical model.
But it's not exactly the same as the Copenhagen model, right?
Copenhagen was just the name of the place where they had the meeting that they decided these things. And
I
Heisenberg,
understand that. But
definitely.
my point is, um, my point is that the Bohr model, maybe to be a little more specific, you had like the Schrodinger, the wave model, but I don't think that the Heisenberg matrix mechanics was a wave model. It was kind of a different view of it, right?
Well, you're probably aware that the Bohr model couldn't explain any atoms other than hydrogen. Once you
Right.
to the heavier atoms, it didn't explain them. So you needed more information in the model, more detail. And the quantum model, well, you went from the Bohr model to the Schrodinger model, which was a non-relativistic quantum model, and then you went to the Dirac model, which was a relativistic quantum model.
Right.
And so there's some variations as you move along that path, but the big question that was addressed at the Copenhagen meeting was: are we going to use physical models, or are we going to use mathematical models? And
they chose mathematical models.
That's right.
And that's where physics went off the rails.
That's what I think. But you say that in like an American Physical Society meeting, and you'll get fired from your job.
Well, good thing I don't work in science.
Yeah. But we have a lot of people that were in the Natural Philosophy Alliance who had the same experience I had in that regard. And it was caught me completely by surprise. I thought people in science were interested in truth. And I found out, no, it's all political.
Well, that really ought not to surprise anybody. I would like to hear what Hans has to say about this.
Well, Dirac has shown that the Schrödinger model and the Heisenberg matrix model are mathematically the same. If you use the Hilbert space as a platform, as a modeling platform, then they are mathematically just the choice between
Okay,
a function space and matrices.
But isn't there a difference in terms of the interpretation? I mean, to say that they're mathematically equivalent, I understand that. That's what most of the books say, that they're mathematically equivalent. But are they physically equivalent? That's the question that I'm trying to get at. Do you understand what I'm saying?
Well, they give the same conclusions with respect to the quanta that comes out of the equations. For example, for the hydrogen atom, they deliver the same shell levels.
Right.
Because finally they come to the same kind of Helmholtz equation and the polynomials that gives you these shell levels. It's the Hilbert space that connects these two approaches.
Which
are you guys able to see my screen now that I'm showing like a picture of like orbitals?
No, you can't see it.
Really?
I see a few colored lines of hydrogen now. So what you promised some time ago, it's now on the screen.
Yeah, it seems that whatever I show on the screen doesn't show up to you guys for like minutes later.
Yeah,
that's going to be highly annoying.
It's not fast. You're right about that.
Okay, that will make it a little bit difficult for me to explain things. Now, eventually, you'll see the picture, the conventional explanation of why the spectra is quantized, and that is they always show like the nucleus at the center, and then they show the Bohr model with the electrons at the various orbits, and they show like an electron going from like the third level to the second level, and every single time an electron makes that transition, it gives off
Franklin, I
energy.
would call this a description and not an explanation. An explanation is that you can show from the origin on what the result will be. And if you don't include the origins of where these lines are coming from, the processes that generate these things, or the model that generates these things, you have no explanation, you have a description. You see these kind of lines and you can combine them with polynomials that exist in mathematics. And that's not an explanation, that's some kind of correlation between mathematics on the one hand and observations on the other hand.
Well, I don't think that's necessarily. I mean, we have the Bohr model of the atom. I mean, that is a physical thing that you could look at with a nucleus in the middle with electrons orbiting around, and if you say that the electron can only exist in those orbits, then that does provide a kind of physical explanation.
Yeah, but then again, it doesn't explain why these photons are coming out of the atom. What is the mechanism that emits the photons? Why do these photons come out of the atom exactly in this way? That would be an explanation. This is just a description of what happens.
Yeah,
I suppose it doesn't go to that level. No. I mean, why should so an electromagnetic wave is a wave, right? So why is it when an electron goes to, say, the third shell to the second shell, why does that produce waves?
the problem is there are a lot of problems with the Bohr model. One is the transition from one orbit to the other has to be instantaneous, no time. But physically, it would take time. The other problem with the model is if I want to have two atoms combined in a molecule, and if they're combined by the interactions of the electrons, then the problem I have is how can it orbit around two atoms and still have these properties? And they can't explain that, and they can't explain how it can stay bound if it's orbiting. And in our solar system, for instance, the interaction of the planets with one another changes the orbits of the planets slightly all the time, and so they can't take all that into account. So that's a problem. But if you use the ring model that Parsons proposed, you solve those problems, and you're able to explain how light can be given off by an electron without moving somewhere instantaneously. What happens is there's a standing wave in the charge of the ring, and that standing wave can make a transition where part of the wave comes off, and it goes to, instead of being two wavelengths in one length, it becomes one wavelength in one circumference. And that, you know how from antenna work and stuff like that, we know how that works, and that agrees with what we observe. And so, but the scientific community did not want a physical model of the atom. They did not want it.
So are you guys able to see my screen with an updated picture yet? I'm showing like a piece of my atomic cubic model. Are you guys still stuck on the hydrogen web elements page?
I see a picture with the description, illustration of transitions, and there
Okay.
are a blue and a pink, and three lines are visible on it.
Okay, excellent. So that's a picture of the Bohr model with it emitting a spectra, and beneath that we see the Rydberg formula, which predicts the major transition lines for hydrogen. So it's a fairly simple formula, which is basically 1 over the squared of the first orbital minus 1 over squared of the number of the other orbital. So it's a very simple kind of formula, and this is pretty accurate. But even though Bohr came up with explain this, like he himself did not know what the origin is. So you've heard from Bill. There's a possibility. We've got the Ring-Parsons model. There's standing waves. That's what is generating the spectra. Although, as Bill mentions, there's masses of problems with this whole idea of there being electron orbitals. If the electrons orbited, they would have to radiate. We don't see any radiation off of neutral atoms, which indicates they're not. And how does this work with molecules? I mean, if they're all orbiting, how can they possibly maintain their stately orbits in larger atoms? I mean, if you've got something like, uranium's got 92 atoms flying around it, it's like, how can it possibly keep track of that?
I have a question for you. Is it, I mean, my view is, this is kind of the conclusion that I come to, or my opinion about it, is that this decision that they made really is to save the point particle electron concept. If you think of the electron as a ring, then you don't have the point particle concept. So I see this as really trying to save the point particle idea. Is that what you think, or what?
Well, it may be. I mean, certainly I think there's an attraction to having point particles that you can draw in a Bohr diagram. But I think personally, now I can give you what my opinion is on why this works, because I don't believe it makes any sense for electrons to be orbiting around the nucleus. So first of all, I reject that idea. Instead, you ever watch Mythbusters? I reject that reality and replace it with my own. And in my reality is that I believe that the electrons and the protons are more of the plum pudding model. I mean, before they came up with all this, before Rutherford, everyone naturally thought that all the electrons and protons were all just all in a big ball. And that's the most natural thing to think, because it's that's what opposite charges are going to do. They're going to just attract to each other and try and produce a neutral matrix. So that's not a crazy idea. Before Rutherford, that's what everybody thought. So I think the biggest enemy was Rutherford, who actually got rid of a seemingly common sense idea.
I'm still want to hear what Bill's thoughts are on my question. I mean, I see the decision made at the Copenhagen conference as saving the electron point particle concept.
They knew a lot of things about the electron at that meeting. They knew, for instance, that it has a magnetic moment. They knew that it has a spin, and both of those are not properties of, and they still acknowledge that in the textbooks. When you do certain types of experiments, you can measure that. The pinning gauge, for instance, you can put an electron in the middle of it, and you can control where it is because it has a magnetic moment. You use magnetic fields to do that, and it has a spin, and you can measure that very precisely in a pinning gauge experiment. But the pinning gauge won't work if it's a point particle. It won't measure these things that we claim are the properties of an electron. And so we've got a lot of logical inconsistencies in science. And I think one of our goals is to identify those logical inconsistencies, so that if we each try to do our own approach, we can see what the data is that realistically we must be able to handle or deal with. And instead of having logical inconsistencies, we should try to get rid of those because we have a better chance of our model being correct or our theory. And so that's what we need to do. And I think that as you eliminate some of these irregularities, I think you'll find there are other benefits to your theory. For instance, when I was working in electrodynamics, and I found I could derive the force of gravity from electrodynamics alone, um, I found that version of of gravity was compatible to some extent with special and general relativity theory, but it was different in that it didn't require dark matter and dark energy to explain the same phenomena that relativity did. And so that was, I considered, a benefit. And it simplifies science. And I think that we should all be looking for things like that when we do our own work, and then share those with other people so that we can see the benefits of the approach you're taking, and that'll give us all a clue as to uh, how perhaps we need to deal with those issues.
Okay, Bill. So we have this issue of that in science, there's no real clear idea about what an electron is as far as visualizing it. And I guess that sort of leads us back into the stochastic visualization of the electron that mainstream has adopted. Does that seem like a fair way to describe it?
Well, when you look at the standard model of elementary particles, like if you look at the string model, the electron is made of strings, and and then when you start looking more carefully at it, you'd say, oh, well, those strings would agree with Parsons' model if they were in the shape of a circle. And so you see a lot of compatibilities and things that are in common between different models. And so, I think that uh, every theory, if it predicts anything useful, has to have some compatibility with other theories that predict the same thing. And so, for instance, uh, if you look at the toroidal ring model of Parsons and you compare that with wavelengths, well, you can talk about the ring in terms of wavelengths around the ring. And so you have that compatibility with some of the quantum mechanics ideas. And so part of quantum mechanics works and part doesn't. But you can see that the physical model can deal with some of those other issues which the mathematical model uh, can't do without creating something new to add to it, to the theory. And so that's what we do. We keep adding new things
Well,
to.
by that, what you mean is what's called an auxiliary hypothesis.
Yeah, we have a lot of hypotheses, but we don't falsify any theory based on its hypotheses or based on its uh, axioms, as the technical term in logic. It's an axiom, and the Isaac Newton said the best way to do it is to do experiments and measure uh, your fundamental laws in terms of like you know the in electrodynamics you have Ampere's law, Faraday's law, Gauss's law, Lenz's law. You take those, and he said what you do is you make those your axioms. So you solve them simultaneously to get a solution for electrodynamics. We didn't do that with Maxwell's equations. We only took 4 of those 6 equations. And so we didn't have anything related to relativity in electrodynamics, which Lenz's law would have given us. Uh, and we didn't have any um, acceleration terms and radiation reaction terms in Maxwell's equations, but you get it if you use all 6 of the empirical equations. So Newton said that's what we should use for axioms. The axiom should be based on empirical laws that we have not found any exceptions to, and we have written down in mathematical form. And so that's one way of making progress. It doesn't always tell you directly, although it seems like when I solve all 6 of those empirical equations simultaneously, in order to get the radiation reaction terms that we observe experimentally, we have to apply a boundary condition. And that boundary condition only works when it assumes the building block of all electromagnetic things is a toroidal ring. So sometimes you get to a place where you get a way of seeing that coming out of the theory in order to make it agree with experiment. But other times you don't get that benefit, probably because your theory is too simple so far. And doesn't
yeah, so a lot of what Bill's talking about does have to do with the specific embodiment of the electron as a ring. So does that answer your question?
Well, I'd like to hear what Hans has to say.
Well, what I understand from electrons is that an electron is a point-like object that hops around, and in that way it generates a swarm of locations, and that swarm of locations that can be characterized by a stochastic process. It is, in fact, the landing locations, the hop landing locations, are generated by the stochastic process, and the stochastic process has a characteristic function. This characteristic function determines much of the behavior of the electron. It determines that it can behave as a probability wave. The platform on which the electron resides is a kind of Hilbert space, and that platform has properties like electric charge and spin. These are the characteristics of the platform, and the elementary particles, inherits these properties. It's the combination of all these things that is doing the complete scene. So it's far too simple. It's far too simple to think about a single thing like a ring or a point or something. It's a combination of things that put together the whole behavior of the electron.
Hans, this is Bill Lucas. When you do low energy electron scattering, you determine the radius of the electron from the scattering, and that radius is what Arthur Compton used, and he determined from the radius that the circumference of the particle was the Compton wavelength of the electron. And that, if you would know what the Compton wavelength is and what the radius is, you can now also predict the magnetic moment of the electron and its spin. And so both of those things have been predicted from the model. You can't predict those properties from the approach you're suggesting.
Sorry. The characteristic function that I was mentioning is the Fourier transform of the location density distribution of this swarm, and so you get a geometric size of this electron, and it has a standard deviation to a certain extent. This is a Gaussian distribution, and this has a standard deviation, and that has some similarity to the Compton radius, this statistical property. So the radius is not a fixed thing, it's a statistical characteristic.
But in scattering, low energy electron scattering below 1 electron volt, you always measure the same size of the electron, and you always find it is compatible with the magnetic moment and the spin. So that
It
gives
is, it
a
is
that's
you're not measuring a single electron.
yes, you
You're
are.
always,
You're
you're
measuring a
always measuring a bunch of electrons, and you
no,
get an average result.
we're measuring a single electron. We can see the electron before and after the scattering. It's a single electron.
So getting back to what Hans mentioned, skipping around. I think that's a very intuitive idea that regardless of the specific shape of an electron, that intuitively we think of it like a particle. We can collide these things together. Electrons can move through space, and he mentioned hopping, and basically the reason why I think we see the specific spectra is not because electrons are in fixed orbits. The reason I believe why we see the spectra is because an electron exists in quantized space, so that an electron cannot exist in some arbitrary position away from the nucleus. That if you instead think of that an electron has to hop from one bit of space to the next bit of space to the next bit of space, that is the real reason why these electrons have these very specific energies. So on a diagram, if you can see it, I have like figure 21. I'm just showing a model of that an electron can only move in fixed steps away from the nucleus. So the black dot there is the nucleus, and the electron can only be like either right next to the nucleus, or it can be 1 block away from the nucleus, or 2 blocks away, or 3 blocks away from the nucleus. And it can't be really anywhere in between. So if you're willing to accept that space is quantized for whatever reason, then that would explain why electron takes what looks like a shell, but it's not really a shell. That the electron isn't sitting there at like the 3rd orbital shell. It can just get knocked up into that 3rd level. It's like if you had a bowling ball, if we dropped the bowling ball, it would drop continuously and hit our foot. But suppose that the bowling ball had to come out of a shelf, and that shelf was either 3, 2, or 1 units high, and we just kicked the bowling ball out of that shelf, and then you would see that when the ball hit the ground, that it would hit with quantized energy, right? So what do you guys think of that idea? That the reason why it's quantized energy is because there is a quantized space.
I think the major error that you make is that you say that the space is quantized. In fact, the probability wave that characterizes the electron, that's the one that's quantized, not space. Space is just there. The probability wave that's representing the electron is quantized. That's a different thing.
Well, I would say that terms like probability wave actually don't make any sense to me. That when I hear probability wave, I'm feeling that is a completely wrong concept.
Franklin, that's your problem.
Well, it is a matter of opinion. I believe that when you're talking about probabilities, that I believe you have gone into mathematics and left the physical world. Now, you could say that that's my problem, but that's kind of my shtick. I always try and explain things in a physical model, things that you could explain on a billiard table or with,
that's
balls
why
and
we,
things like that.
That's why we never comprehend each other, Franklin.
Yes, that is probably why. I mean, but that's okay. That's we welcome all opinions here. So you're saying that I'm not considering the mathematical side, and that's absolutely true. And but assuming that you accept a mechanical model, then is what I'm saying at least sound plausible to you? I mean, you may disagree with it, but do you at least understand that this is one way to quantize the electron energy as it approaches the nucleus.
But you introduced what's known as an auxiliary hypothesis, by saying space is quantized. So you've just introduced a different hypothesis, another ad hoc, assumption into the mix, and saying, well, the existing ad hoc assumptions that physics uses are wrong, and I'm going to put in a different ad hoc assumption, and to me that just, that's not very satisfactory. I mean, space is quantized. That could be, could not be, but it just sounds like a ad hoc, oh, hey, this is what I think.
Well, that's absolutely what it is. So the question is, do you believe the ad hoc Bohr model, which has all these problems we know about?
What Bill said earlier, which is that you ought to have your assumptions based on some experimental, facts. You're using the ad hoc assumption to explain the experimental facts. That's not really proper in logic.
Well, we do actually have these experiments that show that space is actually quantized. Have you ever heard about these neutron dropping experiments, where they get these very slow neutrons, they bounce them, and they find that after they bounce, they can only be in certain locations. I mean, they're not. You would expect them to be continuous if space were continuous.
That doesn't mean that space is quantized.
No, it does directly imply that since the neutrons cannot occupy any particular spot after they bounce, that in fact space is quantized.
A neutron as a wave, as far as I'm concerned.
I mean, why would it only take certain quantized locations if space itself weren't quantized and force them into certain locations?
Because you're dealing with waves.
Well, I suppose that could always be another possibility.
Well, I mean, you're confusing, you're shifting between a particle model and a wave model. And what you're doing is you're saying, well, I'm going to explain the fact that a particle, you consider the electron a particle and not a wave. And then you say, okay, I'll make space quantized. And so that makes my model of an electron being a particle, makes sense, because I say that it can only exist in certain places in space. So you're just shifting around concepts. You're not really, explaining anything as far as I could say.
Well, I mean, that is a potential explanation. That if you like the idea that electrons are particles, and if you like the idea that, they only radiate when they move, and if you like the idea that we see only very specific spectra, and if you like the idea that the Bohr model is correct in that it has something to do with electrons going from different levels, but you don't like the idea that electrons orbit, then, if you accepted that space was quantized, then all those things are solved. So that would be the attraction. Now, you don't have to accept that space is quantized. I'm just saying that this is one way to explain the quantization of the discrete spectra. And to
say that space is quantized, to me, that doesn't really make sense. I would prefer to say that space is discrete and not continuous would make more sense to me. So, your description of space as being quantized is kind of a non sequitur for me. But
well, anyway, I would completely accept your description as discrete. So does that make things better? Space is discrete. Electron can only take certain discrete locations away from the nucleus. Does that make things better?
Well, that makes your explanation a little more precise.
Yes. So what do you think of that explanation now that made it a little bit more precise?
I don't know. Does it agree with the facts? That's the main criteria.
Yes, it totally agrees with the facts.
In your opinion.
But what we have with the Rydberg formula, which is a very simple formula, 1 over n squared minus 1 over n squared. So what is that? So the Coulomb's law is 1 over r squared, right? So if we accept quantized space, and let's say that the electron is like n equals 3, and then it goes, so we know what Coulomb's law says what the potential energy is, right? We can calculate the force. And then if the electron then moves to the second position, like I'm showing here in this diagram, we can calculate what Coulomb's force is at that location, which is, once again, 1 over r squared, or 1 over 2 squared, versus 1 over 3 squared. So if we go from 3 to 2, we just subtract the Coulomb's law force. And that turns out to be exactly the frequency of the light that comes out. The Rydberg formula, the explanation for why it's that form, is because it's just simply subtraction of the Coulomb force of the electron at those two fixed locations.
So the electron's not moving, is that what you're saying?
No, the electron is moving from one position where we can measure the Coulomb force to
So
another.
it's not moving in position 1, and it's not moving in position 2, and it only moves between them. Is that correct? Is that what you're saying?
It's only moving between them. They can move like from 3 to 1, or from 3 to 2, or from 3 to 0. And that's the formula that we have for Rydberg. We're using Rydberg.
So how does the radiation come when it's doing that?
Well, that would be Hans's question, which is why does it generate electromagnetic radiation at that frequency? Now, I can only speculate on how that works. So my wild ass guess is that when it makes this transition and it stops, so it has that potential energy, it must release. And it's a little bit like if you take a tennis ball and you throw it into a box, and you throw it in, it's going to bounce back and forth a little bit, right, to release the energy that you gave it when you threw it in the box. And if you throw it harder, it's going to bounce back and forth faster. And if you throw it slower, it's going to bounce back and forth slower. So I believe that the mechanism for the generation of the electromagnetic wave is simply that kind of bouncing reaction, that when an electron transitions into a new level, it has to relieve itself of its kinetic energy by bouncing back and forth within the little box that it's stuck in, which is the piece of space that it's stuck into. So that's where I believe the actual wave comes from the electron just kind of bouncing against its restriction. And it may actually only bounce really once.
A possible idea is that the electron is losing its electric charge when it is in the atom. If it's moving around in the atom without that electric charge, it will not produce any electromagnetic waves. But all these explanations are human explanations. It is not as the model works. The model works mostly mathematically, and we try to visualize things, and that's our error. We must not try to visualize what's happening there.
Well, once again, I completely disagree with that. I think we totally need to visualize what's going on there. But like I said, that your emphasis is on mathematics. Mine is more on physical model. And those are both perfectly valid viewpoints.
Well, to state my opinion about this, if you don't mind, I'll just throw this out as an issue for me. I don't understand how the electron radiates when these transitions occur. So as an electrical engineer and whose expertise is in radio frequency transmitters and antennas. As far as I'm concerned, I don't think this model that you just said, Franklin, where it goes into a box and bounces around, I don't see that's going to cause any kind of radiation at all. I don't really see, based on classical electromagnetic theory and how we know antennas work or how we think we know they work, I don't really see how, I've never understood in quantum mechanics or in any of these textbooks, any of these models that I've heard of, I don't really see how there's any valid explanation of how the atom radiates. And to me, it's all just, this is so because we say so, but their explanation in my mind isn't credible. I use the word not credible and not convincing to me.
Yeah,
so
it might not be.
Let me finish. That's why I personally am sort of on a little bit what Bill Lucas says about the electron ring model. That makes a little more sense to me because the electron ring kind of looks to me more like an antenna. But that's just, okay, so I've said my thing now.
Yeah, well, I kind of think that if I held an electron in my hand and I waved it around, that would generate EM waves. Do you agree or disagree? If I had an electron in my hand, I waved it around, that would generate radio waves. True or false?
Well, the textbooks say so, but that's not very convincing to me.
Okay, well, you'd agree that the textbook would think that all you need to do to generate a radio wave is to wave an electron around, right?
Correct.
If I wave an electron, if I want to generate a 1 hertz wave.
I can tell you as an electrical engineer, there isn't anybody waving electrons around.
Well, maybe there are. I mean, maybe what's going on in electrons
waving around that I know of.
Well, you might have to consider that, right?
Well, that's
the most basic thing, right? It's like generate a radio.
That's not how antennas work. That is not how antennas work. Sorry.
Well, you just explained to me that you don't know exactly how antennas work. So how can you say that?
No, I didn't say that. I said I don't understand how it works, how an antenna radiates based on how antennas work. So the explanation of how an atom radiates is not anywhere near what we know about how antennas work. So the two are completely different and incompatible. That's my point. My point is that I don't see how quantum mechanics explains how an antenna radiates, how an atom radiates, because I understand how an antenna radiates, and it's not how how they say so in quantum mechanics. That's my problem. Okay, Bill's model makes more sense to me than the quantum mechanics model. That's what I'm saying. Got that?
Yeah, I got that. I'm just saying that to me,
makes absolutely no sense to me because your model is nothing more than I throw an electron into a box and it jiggles around.
Yeah, basically. I'm just saying you jiggle any electron around, that's going to generate EM waves.
You will not get radiation at any one discrete frequency in that model. Sorry.
No, you will. I mean, you will definitely have discrete frequencies because the electron is coming in at discrete energies.
I don't think so. But anyway.
I mean, the whole trick is how do you get discrete energies, right? Now, like I said, that's kind of speculation on my part as to how that thing generates waves, right? That's like, if you asked me to stake my life on it, I'd say, no, I'm not going to do that because it's like, I am basically guessing here.
The bottom line here is that you have a disconnect between classical electromagnetic theory and quantum mechanics, and they try to patch that up with auxiliary or ad hoc hypotheses to sort of make it look like it makes sense. But in reality, it's not very convincing to me as an electrical engineer.
Yeah, it's not convincing to you. And now basically my stick is that I basically disregard all of electrodynamics theory and quantum mechanics and replace it with my own reality, which is, something out of Lego bricks. So, but that's just me. So, as long as you know where I'm coming from, right?
All right, we're not doing science.
No, it's still science, but it's a very strongly model-based science.
You're just making up stuff, Franklin.
Of course, that's what scientists do. We make up stuff to try to explain what we observe.
I proved my point.
So we've got this very interesting empirical data about these.
I want to hear Bill's comment on my thoughts.
Bill, do you have any comments on his thoughts?
Yeah.
Who's crazier,
I want to
me
say
or him? No.
the quantum models of the atom that Hans was talking about, they miss half, 50% of all the emission spectral lines of atoms. In the they occur in the extreme ultraviolet. They were not easily measured on the Earth, but they have been measured by NASA in space, and they're the most precise spectral lines for hydrogen, helium, and all the different atoms. And no quantum theory of the atom can predict a single one of those lines, much less the whole set. And there's just as many of those lines as there are in the other frequency ranges that quantum model was created to predict.
Well, I think it's much worse than that, Bill, because basically they can only predict the spectral lines for hydrogen. I mean, they can't even predict like any of the lines for helium or lithium or beryllium. They can't do it at all.
That's true of the Bohr model, but it's not true of the Schrodinger model and the Dirac model. They can predict. But they only.
Is that true? I don't think that even the Schrodinger model will do anything with helium or lithium.
Yes, they will. They will do all the, but it doesn't get relativistic effects. But it does get the basic spectral lines. And what I'm trying to say is, no known quantum model that uses the kind of quantum mechanics coming from the Copenhagen meeting is known to predict any spectral lines in the extreme ultraviolet for any atom. They miss them all, 100%. And when you do the atom properly with the toroidal rings, you get 100% predictions to the resolution, to the accuracy that they've been able to make the measurements. And the measurements in space are more accurate than any measurement on Earth. So we have the most precise atomic spectral measurements now, spectral lines for emission spectra. And as far as I know, the only approach that can get them is the toroidal ring model of the electron. And a lot of people knew various aspects of the benefits of the toroidal ring model, but they didn't want that model. And I'm claiming that it's a political issue, and the politics was a reaction to a spiritual awakening starting in the 1840s called the Second Great Awakening, and it occurred both in Europe and the United States. And all of our science, I'm documenting that all the major theories of modern science created after 1840 are false by logic.
So Jim raised your flag. Jim, did you have a comment? You want to get the word in here advice? Jim, did you have a question?
I have a question, if I may.
Sure, go ahead.
To Bill. Bill, you still have these lines coming out of the atom, the hydrogen atom, and the what normal physics are saying, these are spherical Bessel functions that determine the lines. What you say is the spherical Bessel functions are not explaining the lines. It must be some more complicated set, not these spherical Bessel functions.
That's right.
Maybe it's a different set, but in principle, the whole thing works similarly.
No, it turns out that in quantum mechanics, if you look at the predictions of quantum mechanics, it can't predict everything that comes from a ring. It can only predict half of what comes from a ring structure of the electron. And so seems to be the difference. No one knows how to modify quantum mechanics to predict the other half of the spectral line.
So what you in fact say is it's a far more complicated oscillation that happens there, but
Yeah.
it's still an oscillation and it still has discrete levels.
Yes, and you can if you we did experiments with um, uh, slinkies, and we were able to show in a science fair project that these um different modes that the electron can have are characteristic of a physical spring, like a slinky, where both ends are attached. So you can have both. You can have different wavelengths in the circular ring that's formed. You can have a wavelength that's the circumference, or you can have a wavelength that's twice the circumference, or three times the circumference, or half, or one third, or one fourth. In quantum mechanics, you only get one of those two options. You don't get both. And so that seems to be the problem. And so quantum mechanics would have to be drastically changed to get the both sets, and no one knows how to do it yet. But that doesn't mean that someone can't find out how to do it in the future. But the physical ring model is different than a point particle moving in an orbit around uh, the nucleus, and you can kind of see that. For instance, the point particle is required by the laws of electrodynamics to radiate continuously, and in every known accelerator experiment where they have electrons going in an orbit, they measure that continual radiation. That's one of the problems with the quantum, where you have the electron orbiting the nucleus. But if you have a continuous ring of charge, it is not required by any of the laws of electrodynamics to radiate. Only when you have a change in the standing wave in that ring are you required to radiate. And so that's a different approach. The physical model seems to do better than the quantum model, and it doesn't violate the laws of electrodynamics because it's really an electrodynamic model, and it comes
Well,
direct.
here's where my question comes in. My question is, and you said it again, you said it earlier. You say when you have the wavelength changes in the ring. My question is, how does that cause radiation? What do you have a model that says how radiation is created when that happens? That's the point. That's my point of skepticism I have with the whole thing.
The wave is moving around the ring at the velocity of light, and when the wave comes off of the ring, when one wave comes off of the ring, it changes the rest of the wave in the ring. And so that there's different ways that the wave can come off of the ring, and that is what produces these additional spectral lines that we see. And um, and it's been
So
a
you don't really have a model. My impression is you don't really have a particular model for how that happens. You just have a kind of a description of the process.
well, it comes from antenna theory, believe it or not.
Well, that's my point I'm getting at. I want to, to me, that's the strength of the argument is that it comes from antenna theory. To me, that's the strength of the argument.
Now, the antenna is going to be a circular antenna, not
Correct.
not a linear antenna. So you have to look at circular antenna data to see how what we
Well, you
observe.
have different modes in the circuit in it. What we call in the engineering world, we call that a loop antenna.
Yeah, and so
And you have modes in a loop antenna just as you have modes in a linear open antenna.
right, and you have standing waves of the charge
Correct.
in that
Correct.
antenna, and certain resonances decay in a certain way, depending upon what type of resonance it is. And so that's what you're seeing in the emission spectra of atoms when they.
Well, I see that as being a more, I mean, I never really, when I read these books on quantum mechanics, to me, it makes no sense how the radiation takes place. This theory basically gives, at least gives a better explanation or a more convincing or more credible, in my view, idea of where the radiation is coming from, how that process is taking place. It's something similar to how an antenna works, as opposed into quantum mechanics, where it's an electron bouncing around.
Yes.
But the radiation only takes place when there is a change of energy level in the atom, and
Well,
that's an instant. It
change,
is not continuous.
change of orbit. Yes.
Yeah. And a change of orbit.
Right.
Otherwise, there is no radiation in the atom.
Right. But unfortunately, for quantum mechanics, no one knows how to make a change in the orbit to produce spectral lines in the extreme ultraviolet. And that's where half of all the spectral lines for hydrogen, helium, and every other atom occur. Half of their spectral lines, emission spectral lines, are in the extreme ultraviolet, and the Bohr model, the Schrodinger model, and Dirac model do predict zero spectral lines in that range of the extreme ultraviolet. So
that's what I claimed. I claimed that physics has no explanation for the emission process itself.
Oh, but
neither for the absorption process.
You see, and one reason why the Maxwell's equations, when they were solved by Oliver Heaviside, he did not take all 6 of Maxwell's equations. He only took 4, because the other 2 put limitations on the structure of the electron and all charged particles. And that structure has to be in the shape of a toroidal ring in order to get the proper terms that we measure for the radiation reaction. You see, regular Maxwell's equations don't handle radiation reaction. And the models for the electron in quantum mechanics do not handle the acceleration or radiation reaction. They ignore it because it doesn't agree with their theory. And so you've got to see things in reality. You can't just look at part of the data and throw away the rest of the data saying, I don't care. If you want truth, you have to take all of the data that we observe into account. And that's what we're not doing. We're not falsifying our theories based on the fact they don't predict all the data. Right? For instance, in the case of general relativity theory, we invented dark matter and dark energy with a fudge factor that was 25 times bigger than the data that was predicted by the theory. You don't put a fudge factor in to rescue a theory. That's not the right way to do work in science. But that's what we're doing. And we're doing it in atomic physics, nuclear physics, elementary particle physics, just everywhere. Astronomy, geology, biology, everywhere we're doing that. And that's not the way to do science.
Can you guys see the graph that I have displayed?
I haven't seen a single one the whole time we've been online.
No? What are you still seeing, Bill? Are you still seeing, what are you seeing on your screen? Because I'm sharing my screen.
I see
I don't know what you guys...
your picture and 2 other people, and then the vast majority of the screen is just black.
Vast majority of the screen is just blank, huh?
Yeah.
How about anyone else? Can anyone see, because I just plotted what the spec lines look like. And this is just a straight plot of do you guys see that?
Screenshots, one on top of the other.
I see the Lyman series, the Balmer series.
Yes, that one. You can see that graph. Do you guys see that graph? Okay,
I see that series.
That is just a straight plot of the observed spectral lines for hydrogen.
It doesn't include the extreme ultraviolet. They won't let you put it in there. No book is allowed to publish it. No science article.
Yes, this is only up to like the bracket series goes from transition level 8 to 5, but it still goes up to the right. So there's still other. I mean, that graph could go up to the right with the Rydberg formula for as long as you want, really. But I'm just showing this because this is just a different way to display the data that shows what looks like a very interesting pattern. Right? So this is what we do. We look at the data, we try and graph it, but I've never actually seen anyone actually do a graph like this. This graph is in the logarithmic, so if things are kind of flattened out, but you can see that there's a very specific kind of staircase pattern we have here for the data, because the problem when you look at the spectral lines, like if you look at the visible spectral lines for any element, I mean, it looks like a scatter chart. It's really hard to see any pattern in that data. But if you plot it this way, which is just showing the transitions to any one ending point, like the Lyman series, that's every single transition where the electron goes down to the n equals 1, the lowest orbit. And starting from, in the way that this graph is done, from the 10th so-called orbit. Now, like I said, I don't think they're orbits. I just think that's just quantized distance away from the nucleus. So every single time an electron falls from like 10 units away down all the way down to 1, that's what I have graphed here. And so it follows a very interesting path. Now I've done this for the other elements, and those also generally show a very similar pattern. Like I said, that for just even helium, they don't have any equivalent for the Rydberg formula for even helium.
There are
But
books. There are books that plot these things for all atoms from 1 to 100 or so.
Yes, I mean, there's definitely, and that's what the data I have here. This is stuff I pulled off from NIST. But you can organize them in a similar manner. And actually, for helium, there is a modified Rydberg formula that if you take all the electrons off of helium except for one, so that it only has one electron bouncing around, then there's a modified Rydberg formula for that. And that's basically what I have plotted here, is that you've got the plot of the emission spectra for helium. Now, what I did is I took this one step further. Was that, lithium is just like, that's lithium is very much more complicated. And if you go and you basically make the assumptions that the spectra is being generated basically from this difference of Coulomb force, then you can go and identify the patterns that you see for even lithium. And so lithium, the spectra from lithium can be described with Rydberg-like formulas. There isn't any super precise formulation that you can give to it, but certainly you can go and identify close to 80-90% of the spectral lines that will fit into these formulas. So the point being that you can actually calculate the spectrum of lithium in a similar way that we calculate the spectra for hydrogen. It just gets a little bit more complicated than that. I made a chart showing what would be the observed spectra and what would be the calculated one, and the percent differences are very small across fairly wide range. I mean, there's some that are not that particularly accurate, but it's just an interesting point of information. Now, curiously enough, in academia.com, this is actually like my most popularly read paper about explaining the spectra of lithium and beryllium, and you can actually go and do things like carbon. So, but basically the formulas, you just have to come up with different sets of formulas that use different constants. So instead of just plain 1 over r squared, you'd have to do r squared times 0.13, And then for the different levels, there are still variations, but it's still, and that's kind of, it is admittedly kind of like, curve fitting, right? It's like you can find a formula that fits the data if you work on it hard enough. But it is interesting that it may be possible to determine formulas like that. So I don't know whether you guys, can you guys see the screen that says conclusion on it? Because on the left-hand side of that, I show a set of possible Rydberg-like formulas where you can explain all the observed lines for lithium. But so I just bring that up as a possibility because it's predicting what these spectral lines are. I'd never really seen anyone try and do something like this, except for Bill Lucas's work, where he goes and he has formulas for the extreme ultraviolet, and those look a lot like these other formulas that I'm coming up with. That they are basically a subtraction of Coulomb forces, which what I believe is the actual origin of the quantized spectrum, and no matter what really model you believe, that it has something to do with the Coulomb force. So I would just throw that out as another interesting point of view. Bill, what do you think of that? Can you predict spectra of lithium using Rydberg-like formulas?
Yeah, but when you get into some of the more sophisticated effects, you won't get them from the Rydberg formula, but you will get them from Schrodinger or the Max equation. By the way, if you were to use the Rydberg formula for hydrogen and try to do the extreme ultraviolet, you would find instead of the n equal 1 and 2 that you have in your formulas, you would have n equal 1/2, 1/4, 1/3, that kind of thing. So it'd be upside down. In other words, and the Rydberg formula can't predict those numbers. It can only predict 1, 2, 3 for the n values. And
yeah, I noticed that your formula, the actual mechanical format of it is still Rydberg, but you have different factors in front of things.
right, those factors are due to the fact that we have a ring, and the ring can have around its circumference a single wavelength, two wavelengths, or three wavelengths, or it can have the wavelength being 2 revolutions of the ring and 3 revolutions of the ring, and that sort of thing. So what is happening to the Rydberg formula is it can't take both counts, both types of things into account simultaneously, whereas the ring model can. And by the way, the ring model has experimental basis also. It was based on the work of Arthur Compton and also his last graduate student, Winston Bostick, who made these toroidal rings of different sizes so he could perform experiments with them. And that's what he did, and he was able to show some of the type phenomena that we're talking about.
Okay, well, we're getting towards the end of our conference here, and following this conference is a new conference for the Earth tectonic groups. So I invite you to switch over to that conference. And I also included a link to that conference in my announcement. So and the links inside of the CNPS website, I don't think they were quite correct. You have to type in the conference number manual. Don't use the links, not unless you use the link that's on my mail message, which I made sure was correct. But we've been talking about atomic data, and I don't think that. Yes, go ahead.
No, one of the pet peeves that I have is that when one gets a textbook on physics, one never sees any experimental data. They don't talk about experiments, it's all just 100% theory, and the assumption is that you have to do your homework to figure out whether or not anything that they say in the theory is actually correct, and you have to dig up all these papers. Do you know of any good books in physics that one could look at that actually deals with experiments and talking about experiments and not just one, theory?
Well, there is one book that I have that you can obtain on the internet. I can certainly send you a link to it, which explains all of the physical data. Well, I mean, hopefully he would point to the same book that has physical data and explains the shell and the liquid drop model and the problems with that. But if you want data, I mean, it's out there.
You could. I'm just wondering. I just am curious. Bill, what are your thoughts on that?
Well, I had to publish my own papers in places like Galilean Electrodynamics and some of the European conferences I went to, Soviet Academy of Science, stuff like that. Places that would allow you to publish and present the papers, whereas in America they won't. They don't like it.
Yeah, but what I'm asking well, Franklin's cited a book, but whenever I read a physics book, I don't see anybody talking about experiments. It's all theory. I mean, is there any good books out there that can introduce people to these issues of what is the experimental basis? I mean, you talked about all these experiments that you know about, but we don't know about them because we can't read about them.
In the 80s, I used the book with absorption spectra. It was about 200, 250 pages thick of lists of these data that we just saw as small graphs, and they had them for nearly all atoms that are known at that time.
Yeah, a lot of the raw data is available. Although it doesn't sound like Bill has a specific book he can recommend.
I'm interested in a book that talks about experimental physics that can explain to you like how all these experiments are done, and I mean, I don't think there's a book out there.
I don't know if there is a book out there, but I could send you some links.
I'm not interested in data. I'm interested in, how the experiment is done. How do they claim they verify the theory? I don't think it exists in science.
It may not exist. So,
well, I'm writing one.
I'm asking Bill.
Yeah, Bill's writing one. When Bill's one done, then you'll have a book. But I really have to close the conference here today. So we've been talking about mostly emission spectra and where that comes from. So Bill explained his ring model. He thinks there's a lot of things that can be explained about that. I also shared with you the existing Bohr model and why there's some problems with that. And I shared you my own opinion on where the emission spectra comes from as a result of quantized space is another possibility that we could consider. But that, I believe, will do it for today's conference. And I would like to thank all of our participants and asking interesting questions about, what is an explanation and what has science been doing and where did they run off the rails. I think that's all important discussions to be having. And but that will do it for this week's conference. And like I said, following this conference is the Tectonics Conference. So I would invite you to log out here and hop onto that conference. Once again, I have the link for that conference in my original invite. So everyone have a good week.
Bye.